Welcome everyone to my talk on writing UEFI applications with C++ or modern C++. My name is Morris Hafner. I moved from Germany to Scotland to eat haggis and work on compilers. I'm a software engineer at CppCon, where I work on sill, the kernel standard for heterogeneous programming for C++. I'm also a postgrad student at the University of Edinburgh, and unfortunately I also have a tendency to break compilers, debuggers, linkers, pretty much you name it. And I like to say that it's a curse, but it's probably also because I want to do fairly exotic things, like trying to make modern C++ happen on exotic platforms like UEFI. So what is UEFI? It stands for Unified Extensible Firmware Interface, and it's meant to be the replacement for BIOS on the PC platform. So it was initially developed for the Intel Itanium platform in the 90s, and you all know how that went down. But the technology was reused for x86 and can also be used for ARM and RISC-V-based computers. It has many more features compared to BIOS. You have network access, you have security boot, which was quite controversial in the Linux community. You also have non-volatile RAM. There's even a bytecode specification if you want to share application code between different CPU architectures. But the most interesting thing about UEFI compared to BIOS is that you don't need to write as much assembly code anymore. So can I give a shorthand? Who has written code for BIOS? Maybe a bootloader or kernel? Yeah, a couple of people. So you might all be familiar with this then. So the BIOS was the initialization system, so to speak, for the original IBM PC. And what happens if you press the power button until UEFI is that it does some very basic initialization on your mainboard, then loads the first 512 bytes of code from the master boot record, jumps to some specific address, and then you're on your own. And even very basic things like switching from the 16-bit mode to 32-bit mode to 64-bit mode and so on, you have to do it yourself, and this obviously will require assembly code because switching to 32-bit mode isn't covered by the C language. So it is much more lower level, and you have to call interrupts instead of having proper functions like you have in EFI. So EFI executables are just binaries on some FAT32 partition with a very specific file system code. As you can already see, it was heavily influenced by Microsoft doing standardization because it uses the same binary format as Microsoft Windows. It uses the same calling convention as Microsoft Windows, and unfortunately also uses UTF-16 strings, which causes a headache. And when you press the power button on pretty much every PC here in this very room, including MacBooks, it does some initialization of your hardware, like BIOS, but then doesn't jump to some address, but launches an executable, which is usually located in EFI/boot/bootx64.efi. So this is usually the case. You may change the default. You may also have to deal with broken implementations, like the one on my laptop here, which just hardcodes the path to the Windows bootloader, and this is an interesting exercise if you want to install Linux on this machine. So how do we get an executable to run on this platform? So first of all, we're going to need some kind of toolchain. So the thing you usually want to use is the Tayano Core EDK2, which is just a truly massive framework and contains functions for all kinds of things. It even has a port of Python 2. So if you want to run Python 2 without an operating system, download EDK2. But I wanted to have something simpler than that. You can, so I went with the GNU EFI lib, which is pretty much just a set of headers, a static library, a linker script, and some basic functionality for certain C language features in the CRT0. As for compilers, you can use MSVC. I'm going to use the MinGW GCC, but you cannot use Clang. If you try to use Clang, you get a nice error message saying that freestanding COF executables are not supported, and you get a nice internal compiler error afterwards. Right. So the standard library. So we have an SDK, we have a compiler, now we have a standard library. Or we need a standard library. Unfortunately, we don't have one. The EDK2 ships with an implementation of the C95 standard library, which is pretty much just a C90 library with some bug fixes, and the ISO 646 keywords, so and, or, bit, and so on. But we also don't have a C++ standard library. So things like operator new, dynamic cast, RTTI, everything that requires runtime support is just off the table. But in practice, and this is very, very hacky, we can still reuse things from our hosted implementations like std array, std tuple, or the type traits, because those are just compile time constructs that don't have any dependency on the runtime. So it's hacky, but it works. And I just went with that. And with that, we can finally compile an executable. So your compile application line will probably look like that. You want to invoke your compiler. You want to disable the red zone, which is an optimization in the x86 64 calling convention. And this allows certain small functions that use less than, I believe, 128 bytes of stack space to not decrease the stack pointer, even though you're using stack space beneath the stack pointer. But we are on a freestanding environment here. We don't have an operating system that would catch all the interrupts. And if an interrupt occurs on a system, what happens is that the processor wants to save its state on the stack. And if we didn't decrease the stack pointer, we will cause memory corruption. So we have to disable this optimization. Next. So as I said, we are in a freestanding environment. We have no operating system. We are in Microsoft Universe, where wchar is 2 bytes and there are 4 bytes. We don't have standard library. We need to change the entry point from main to something else because the signature is slightly different. And then we tell the linker that we don't have a Win32 executable. We have an EFI application, and we tell this we are saving this information by setting the subsystem of our application to 10. So otherwise, Windows would just think that this is valid Win32 application. You could launch it on Windows and it would horribly crash. I can put this in a CMake toolchain, and then we can finally compile code. So hello world looks like that. We include 2 headers, EFI.h, EFI-lib.h. Our entry point is extern C and use the Microsoft ABI. And a very important thing is here the system table, which contains all the services you can access through the EFI. For example, conout to print out strings on the terminal. So I create a UTF-16 string with hello world. Unfortunately, I also need to cast the const away because the interface is broken. But yeah, this is hello world for UEFI. And you compile this with the command line I just showed you here. And then if you want to run it, you can download OVMF from the internet, which is an open source implementation of UEFI and is compatible with QEMU. So you can just set it as the firmware for your QEMU virtual machine. You put your executable inside of a virtual hard drive with a FAT32 partition, and then you can hopefully launch your Hello World application inside of a virtual machine or actually on real hardware if you would like to do that instead. So I've already shown you the conout thing, and there are obviously many more features than printing something out of the terminal in UEFI. And if you would like to have access to some service, you usually need to query for its existence using GUIDs. Because, for example, if I want to render something on the screen, I need to have a graphics card installed on my system. Not every system has a graphics card installed on the system, so this might fail. So we need to query for the existence of certain services. If that succeeds, we get a nice struct back, which contains a bunch of function pointers, and this gives us a nice object-oriented style interface, even in C. Nice. Yeah, nice in terms of C. We're obviously biased here. And if you look closely here, the signatures are very, very interesting because we always have a return. We will always return an error code, EFI status. We have some input parameters, we have some mutable parameters, and we have some output parameters. So Windows developers might be already familiar with those in, out, and out annotations, and in EFI you have the same. So that's very interesting. because in C, this is probably fine and the thing you want to do. But in C++, we are more used to interfaces like that, where we return all of our actual output arguments by value and usually don't want to deal with any error codes. So what we would really like to have is a function that takes all the input arguments by value, or by constref for that matter, the mutable arguments by reference, returns an expected of a tuple, or my error code, and then I have a much nicer interface. Because the other thing about output parameters is on C, you need to create your output variables on the stack right before you make a call to the function, and those values in there don't make sense. And we can't mark those as cons because we are only writing to them in the next statement. So it's just an error-prone way to call your functions. So how do we improve that situation? I'd like to create a wrapper for all those UEFI functions, and for that I came up with a function called wrap that takes an UEFI function or UEFI function pointer, takes 3 integers as template parameters, the number of input arguments, the number of mutable arguments, and the number of output arguments, and then I like to pass in a function pointer, and then I get a new lambda back, or a new function back, with my fixed interface that is more C++y. For this to work, I need to do 3 things. First of all, I need to get the list of all my argument types. Then I need to split this up. So I have my input arguments, the mutable arguments, and the output arguments separately. And then I can finally create my init function, and then we can add some error handling to that. For the first step, we need to get the argument list. My advice is don't bother with it, just download Boost callable trace and use that instead. It has a really nice type alias called argst, where you pass in a callable, in my case locate device path, or the type of locate device path, and then it returns a tuple with all the arguments. And then with this, the next step would be to split up this tuple so we have our inputs, the mutables, and the outputs separated. And we can do this with a cons_expr function like that. So my idea is that I implement a one-way split. So given a tuple, I want to have a new tuple that contains 2 tuples, where the first tuple contains every element from 0 to n, and the second tuple contains all elements from n to the end. And C++14 with make index sequence makes this actually very easy to do. I just call make index sequence with n for the first tuple, and then call make index sequence again from n to the end for the second tuple, and forward everything to the st_impl function that basically just copies everything into my new tuple. Note that I actually don't call this function. This is all just to get the types right. And here I do my final 3-way split. So here I'm just creating a bunch of type aliases that don't cause any runtime code. And here if I have my argument list and I want to get the first part, all my input arguments, I just do my split at the number of input arguments, and to get the mutable arguments and the output arguments, I need to do this. You need to split the second tuple at the number of mutable arguments, and then I end up with 3 meaningful type defs here: in containing the input arguments, in out containing the mutable arguments, and out containing the output arguments. And with those 3 type defs, I can call another cons_expr function called make out param adapter that takes 3 variadic templates: the sequence of inputs, the sequence of mutables, the sequence of outputs, and it takes the UEFI function as a parameter here, and returns a new lambda that captures our UEFI function, and this lambda only takes the inputs and the mutables as an argument, but not the outputs. The outputs are just locally allocated on the stack here. So I remove the pointer type and create a tuple of my result. Then I create a second tuple temporarily just to get my pointers back to my result here. So now I have my inputs, my mutables, and the pointers to my outputs. I concatenate those three, pass everything to std apply, and then can call my EFI function with my reconstructed tuple, and then I can return this tuple, the tuple of my output arguments. So I have a question. Who thinks this causes any overhead? We have one hand, two hands. Okay. So most people were wrong. We have overhead. So here I have a function f that has a single output parameter, and then I came up with a wrapper that I would probably write in C. So it returns an integer, allocates an R on the stack, and returns the result. And then this is the CPP function is something that is more similar to what we just metaprogrammed. So we allocate a tuple of int and then return a tuple of int. And you can see on line 11 that we have a dead store here. So we move the 0 to some address. So we have some overhead here. And the reason for this is that the tuple causes value initialization of your functions, which means that in our case that the integer is initialized to 0, whereas in C, this is just an uninitialized value. But the compiler cannot optimize that out because we're wrapping an opaque function pointer, and the compiler can't determine that we actually only write to this memory address. We never read from it. In C, that's easy to tell the compiler because we just say, okay, this is uninitialized, we just optimize it out because it's undefined. In C++, we set it to 0. The compiler has to assume that this may be read from some other function. It can't optimize it out. How do we get around this? We can just create a small wrapper, which I call uninitialized, that has an empty, explicit default constructor. And when we value initialize this struct here, this does only default initialize our value. So initialization is unfortunately hard in C++. And we can just grab all of our output variables in this uninitialized type, because we are sure that we want to have uninitialized values, and pass this to our function. So minor change, and this instruction goes away.
If you've done equals default instead of int braces, have you gotten the same result?
I believe the overhead still doesn't go away because this still causes. I believe this still causes value to be default or value initialized, but initialization. Okay, Chris says no. I believe him.
Okay. That's good. I know you're pressed for time.
Yeah. Okay. And now what we still need to do is wrap the error codes. So as I said before, we don't have access to exceptions, and even then exceptions cause some overhead, so I don't really want to use them. Instead, I want to use an expected type. So if you haven't seen Simon Brand's and Phil Nash's talk or Andre's talk from earlier this conference, an expected type is something like a special variant that either contains a result value or an error value. And in my case, I'm using Simon Brand's implementation, TL expected. And now we just need to extend our wrapper with a small ifconst expr. So we check if the return type of our function is EFI status, so it can return an error code. And if it can return an error code, we call our function, check the error code, check if it's not EFI success. If it's not EFI success, which means there's some error, we return only the error code as an unexpected value. Otherwise, great, we have a success. We just return our tuple instead of the expected. Then there's also this case where EFI functions don't have an error code that they return, they just return void. In this case, we can just return our tuple directly without wrapping it in an unexpected. So, question number 2. Overhead. Who thinks this causes overhead? No one. Okay. Oh, okay, never mind. Okay, so I can't show you that, but what I essentially did, I put my entire wrapper inside of Compiler Explorer. I wrote the same wrapper basically in C and C++. So I just called my EFI function, and in C I create my output variables on the stack. In C++, I just call my wrapper. And then I check my error code in C, so I see if something failed. I print out an error message. If it's conceded, I print another error message, and did the same in C++. And the result was that the generated assembly code is indeed different, but only because the compiler inverted the jump instruction. So unless you want to take something like branch prediction into account, it doesn't really cause any overhead. Right, so this was the metaprogramming part, but I still want to make some things very clear. I made a lot of simplifications and assumptions. So first of all, I only have a 30-minute slot. I can't cover everything. Secondly, I'm wrapping C, not C++. I made assumptions that we are only wrapping fundamental types and ports. I believe the compiler has a much harder time optimizing things if things are not trivially copy constructible, for example. Also, the trick with the callable traits only works because we don't have any overloads. I'm only wrapping C. C doesn't have any overloads. But you may want to add overloads by yourself with a feature-listed overload when you're writing a high-level wrapper using my wrapper, for example. Okay, so I've shown you a bunch of metaprogramming, but I still haven't really shown you on how to write some non-trivial application that is not Hello World. So we could write our own kernel now, or we could write our own bootloader now. You just call exit boot services, and the machine is your own. But I chose to render a couple of things on the frame buffer instead, and I don't think, because of time, I don't think I have the time to show you that, but I can just show you later after the talk. But yeah, first of all, I need to create an instance of the graphics out protocol. So as I said before, we are not sure if our hardware actually supports graphics. So first of all, we need to query for the existence of some graphics adapter. And we do this by, first of all, creating two wrappers. So we need two functions, locate handle buffer and handle protocol. And with those two functions, we can finally create our instance. So I call locate handle buffer, and if that succeeds, I call handle protocol, and if that succeeds, I cast the result of handle protocol to EFI graphics out protocol. And the nice thing is, if anything fails, I just print out fail, and I'm done with it. And the nice thing is, even though we didn't have exceptions, I could put in my error handling inside of my slides because I use expected. Okay, so with our graphics out protocol instance, we can create a frame buffer, which is just iterating over the available modes, so different resolutions, different color depths, and so on. In my code, I just chose to choose a very specific resolution that is pretty much available in every system. If it doesn't work, I'll tough luck, I just exit. And yeah, we created our frame buffer. We can actually draw to the screen now. So in my case, I also wanted to have some double buffering, so I emulated by just stack allocating enough space, and then implementing two functions, swap the screen and clear. I'm also using std fill and std copy because those I don't have any runtime dependencies either. And with that, I can render things on the screen. And unfortunately, I still don't have access to the heap because I was mostly just too lazy to do it. I could just probably re-implement malloc. But yeah, I can't just open, say, a GLTF file from the hard drive, do some mesh processing in memory, and then render everything on my screen. I only have my stack, but implicit surfaces give me an escape hatch. Implicit surfaces give me a functional representation of my scene, and with that, everything is just a function or stack allocated, and I can just ray trace that scene. Fortunately, no time for details here. I can show the demo after the talk. But yeah, this was basically the talk on UEFI, so I want to cover a few more things. Everything I've done here was technically incorrect and non-conformant. Mostly because, partially because I made a bunch of hacks, but also the standard, even if we have a C++ standard library available for UEFI, the standard says about freestanding environments that the available subset of functions available is pretty much just the subset of the C standard library. Right now, yes?
So that's not exactly true. The way the standard specifies the freestanding mode is at least those headers. So your implementation is absolutely allowed to provide you more than the bare minimum that the standard specifies.
Okay, so to paraphrase, Michal pointed out that an implementation is allowed to provide more features from the C++ standard library. The standard just mandates that it has to provide at least more or less the C subset. Was that more or less correct? Yeah. Okay. So right now, to fix that, there is the SG14 meeting happening right now, and one of the papers on the agenda is Ben Craig's proposal for freestanding environments that tries to mandate more classes to be available in freestanding environments. Because when I'm writing the tuple, why am I not allowed to use the tuple when I want to make sure that it works on every freestanding environment? And there's another interesting paper going on right now, the zero-cost deterministic exceptions by Herb Sutter. And those allow us, it basically reintroduces something similar to the exception specifications, and this will probably allow us to write throw and catch statements, but everything will just map down to a language built in expected type, so to speak. So maybe in the future we'll still be able to throw and catch even if we don't have access to the heap or any other language runtime features. So yeah, those are my references. So you can check out my code here on my GitHub, mmh/EFI raytracer. If you want to learn more about UEFI in general, I definitely can recommend checking out the OSDev wiki on UEFI. There's the freestanding proposal. There is the implementation of expected by Simon. And yeah, that's it. Thank you. So, to much surprise, we have 1.5 minutes of questions. Yes, Jason.
At the very beginning on your EFI main, it looked like you had a C++ attribute in your extern C EFI main, and I was just curious if that's actually what that was, and if that was...
So the question was about the... Right, this GNU MSABI thing.
Yes.
So the thing about GCC is that most attributes are also available as C++ notation. So you can also write __ attribute in GCC, but I think that's ugly. I just chose the C++11 notation.
So your pilot was fine with that?
Yeah.
Okay.
Yes.
So one thing you can do to use Clang for this is to build an ELF file and object copy it. And it actually works, and you don't actually have to worry about like dealing with Microsoft formats on Linux.
You have to manually relocate the symbols if you do the. I know because I just did it.
Object copy works if you do it correctly.
So the comment was that I can also use Clang by using object copy.
Yeah, but
that's even more hacks. I won't do that.
Linking to our, that's literally what that program is created for.
Sure. Okay. Yeah. So thank you very much.